All right, guys, so week 8, lesson 2, right? This is going to be some pretty new stuff. Once I get down there to that really new stuff, I want you guys to, try your best to pay attention and grasp the concept. But I'm not going to dive too far in. I don't want to waste too much time on this video. So if you really need help and stuff like that, then I encourage, the tutoring times and stuff like that in order for you to get a better understanding of it, right? But for now, let's just kind of dive in. So we're going to start with exponentials, right? So there's two different types of exponentials. There's exponential growth and there's exponential decay, right? Exponential growth is going to have a base, right? That's that number that is attached to that exponent, is going to have a base greater than 1, right? Greater than 1. While exponential decay is going to have a base that's greater than 0, but less than 1, right? So it's going to go just like that. So keep those things in mind as we go through this, right? Because those are going to be really important. First and foremost, let's start with this number 1. Oops. This is really easy. This is just evaluating, right? This is as simple as plugging in numbers and solving, right? Plug and chug. So we have 4 times 6 to the x power when x equals 3. So all that's going to happen here is 4 times 6 to the 3rd power. We're just plugging in that 3 for x. Then we just solve using PEMDAS, right? So parentheses, right? No parentheses. Exponent is first. So we're going to take this 6 to the 3rd and solve that first. So we still have this 4 times whatever quantity this is going to be, and 6 to the 3rd is going to be 216. 216. Then I can do 4 times 216. 4 times 216 is going to be 864. And that's it, right? You just plug it in and solve it. Really no big deal. Really what they want you to know here is order of operations. They do not want you to do 4 times 6 first and then raise it to the 3rd power. Hopefully we're well aware of order of operations and we're able to do that with no problem, right? So make sure you do that exponent first and then multiply afterwards, okay? Down here, okay, so this is where that exponential growth, exponential decay stuff comes in handy, all right? So definitely have those definitions handy. Tell whether or not the following function is exponential growth or exponential decay, and then sketch its graph. And the sketch is going to be really quick. Hopefully you guys remember the stuff I taught you about the parent function last week, because that's going to really come into play here. Okay, so our base is 8, which last time I checked, 8 is greater than 1. So we have here exponential growth. So we have growth here. Okay, so that exponential growth is going to look just like this, right? I'm going to have the XY axis here. And so the thing is here, remember last week when I talked to you guys about the parent function, I told you it always goes through the y-intercept of 1. And then that's because 8 to the 0 power is 1. And then when we plug in the 1, x equals 1, so right at this tick mark, the y value is going to equal whatever the base is equal to, because 8 to the 1st power is just going to equal 8, right? So when y equals 8 to the 1st power, that's just 8. So my ordered pair here would be 1, 8. So right here at 1, I've got 1, 8, and we're just going to call 8 being up here. And so that's going to be the two basis things of my parent function. Parent function, not quite a parent function anymore because we changed it, but so that's going to be my 2 points. So, and it's just going to look the same exact thing as the other one. So it's going to be really close to the x-axis. It's going to turn there, and then it's going to shoot up because that base is so large. It's going to shoot up. So actually, yeah, we're just going to keep it like that. I know that's super ugly, but that's okay. And that's what it's going to go through. So really just those 2 critical points. You want to know the intercept. That's horribly written. So you want to know the intercept, and then you want to know the next pair, x-ordered pair, right? Next point. Okay, so as long as you know those 2 points, you're going to be just fine, right? So let's hustle down to this one, number 3. Now 1/3 is our base, so now 1/3 is in between 0 and 1. So to start, we should know automatically, okay, well this is going to be decay, and it's going to be a little bit different than what you're used to, right? You're used to seeing that exponential function increase as we go from left to right. This one's going to be a little bit different. So this one's going to decrease as we go from left to right. This is going to look like a reflection across the y-axis, which makes sense if we think about it, because if we were to make that x negative, then I'm not going to dive into the why it makes sense, because that's a whole different lesson. I don't want to waste you guys' time, but if you're interested, I can definitely dive into it, and it makes perfect sense, right? Algebraically, for this to flip across that y-axis makes complete sense. We can do kind of a play-by-play of why that is. If you're interested, you can come into tutoring, stuff like that. But let's just kind of dive into how to do this so I make sure I'm not wasting anyone's time. Okay, so what's happening is this is still going to have an intercept of 0, 1. That won't change. But now instead of going to the right and finding what is happening when it's equal to positive 1, we want to go to the left for decay and find when it's negative 1. Okay, so what's going to happen is, just because it's going to be a little more clear this way. So when I plug in a negative 1, so let's find this. So let's go 1/3 to the negative 1 power. Remember, that negative just means I'm taking the reciprocal of whatever's on the inside of those parentheses. So when I flip 1/3, I get 3/1, which is just 3 to the first power. And last time I checked, 3 to any number to the first power is just itself. So my ordered pair here is -1, 3. That's my point. So I'm going to come up to 3 here, and that's going to be my second point. And now I've got exactly what I need. Again, it's going to look just the same, except it's being reflected, so it's going to come over like this. And again, that should go through that point, sorry. But yeah, so exponential growth is over time, things are going to get bigger, right? As I go to the right here, things are going to get bigger, right? The right really implies going forward in time, right? As you increase in number. Decay, as you increase in number, it's going to be going down. It's going to be getting closer and closer to that x-axis, right? Over time, it's going to be decaying. It's going to be losing value or whatever we're talking about in the context. So it will be going the opposite way, whether it's growing or whether it's decaying. Okay, let's come down to converting functions into their kind of, I guess, standard form, you can call it, of exponential growth or exponential decay. Okay, so looks like I messed this up a little bit. So this should be, these x's really, guys, should be t's. So let's kind of zoom in and fix these really quick. Sorry about that. These should be t's. Okay, now that that's fixed, we can kind of get going here. So the standard form of these exponential growth, exponential decay things is A, which is your, so think of these as kind of your interest problems, right? Whenever you go to the bank, or I don't know if you guys have been present when maybe your parents have bought a car, or if you looked into getting a car, all that kind of stuff. But there's a value on that car that you buy it for, but then when you're paying back the bank, if you're financing through a bank, you're paying them more than what the car is actually worth. That's because of interest, right? Depending on your interest rate is how much you're going to pay a difference of what the car's worth and what you're really buying it for, right? This is pretty much how they compute that. So they tell you, well, we'll give you a rate of 3% per year, right? So that should be a really good rate. But 3% per year, so this is kind of what they kind of plug in to see what you're going to be doing over the however many years you're financing for. So it's exactly that. So this is really important. This exponential growth, exponential decay problems in these forms are really important. You can kind of find the exact rate that they're going for, all that kind of stuff. So let's kind of dive into this. We just want to convert it into that function form. We don't want to solve anything. We don't want to make this more complicated. We're just going to make it look like this guy up here. Okay, so this is exponential growth, this number 4, because the 5 is greater than 1. The base is greater than 1. So it's going to get plugged into this guy right here. Okay. So this is, bear with me here, because this is going to take a little bit of exponent rules for this to make sense. So I have y equals a 5 to the t over 4. Okay. I want this to only be a t up here. If you look at this function, I know I messed it up at first, but we just want the t by itself on the top here as that exponent. We don't want a t over 4. We don't want that. All we want is the t by itself. So this is a quick conversion, but it's easy to get confused a little bit. So I'm going to kind of change colors here just a little bit just to see if this makes sense to you. So I'm going to pull that t out. So as you guys know, I can take t over 4, or I can take 1 over 4 times t over 1, or just t, and that kind of splits up this t over 4. If I were to multiply these two together, I would get t over 4, right? Hopefully you guys see that, because that's essential to this making sense. Okay, so if I were to multiply those two things together, I'd get t over 4. So really, in actuality, I can separate those two. I can kind of pull those apart here. So I'm going to keep this original function. So I still have this a to the 5, and then I'm going to pull those apart. So I have 1/4 as its exponent. And remember, when you multiply exponents, that means you're raising an exponent to an exponent. So I'm going to raise all of that to the t. Now this is starting to look a little bit like what I want, right? I want there to be a base raised to just the t. Now all of this blue stuff in here is the base raised to a t. So now I've just got to simplify this base a little bit. I've got to make this base, this 5 to the 1/4, look like this 1 plus r. So let's go ahead and solve that. So 5 to the 1/4, I do not know off the top of my head, contrary to you know, how good I am at math, I don't know. So let's plug that in over here. 1/4. That is going to be, as it thinks a little bit, oh my goodness, it's taking forever. Okay, that's going to be 1.49. Let's just call it 1.5. Okay, let's call it 1.5. That's a rounded version of it. So that's going to be equal to, the a is still there, but on the inside, I've got now 1.5 raised to the t. Now hopefully you guys can separate this and just subtract a 1 out of it and put the 1 out front. And so my final answer here, let's put it in pink. My final answer here, this is going to be y equals the a. 1.5 I can separate and say, well, 1.5 is just 1 plus 0.5. And then I've got it raised to the t. And that's it. So yes, it's a little weird, and this is what I'm talking about when I tell you guys, you know, that I'm going to be running through these concepts. These concepts make a lot more sense if you spend some time with it. But like I said, I don't really have the luxury of time for these videos. So if you really want to get into this, then make sure you are coming to tutoring, asking your teacher, all that kind of stuff. So let's move on to the next one, number 5. Same exact idea, same exact thing. So this one's actually going to be exponential decay, because that 0.04 or 0.4 is going to be greater than 0, less than 1. So it's going to be plugged into this guy right here. Sorry, my pen stopped working. Right there. So let's go ahead and do that. Okay, so again, I'm not going to rewrite it this time. We kind of know the process of this. I've got to separate that t over 12. So I know t over 12 is equal to 1 over 12 times t. Right? We know that. So that separation is what's important. So I'm going to do that separation. So I still have that a. And then I've got this 0.4 to the 1. Oops, sorry. I didn't mean to do that. Yes, I did. To the 1 over 12. And then I've got to raise that whole thing to the t. Because remember, t times 1 over 12 would be t over 12. So I've done nothing to the value of this function so far. It's the same exact thing. Right? And let me actually kind of square this off, because it has nothing to do with what we're doing. So then I've got to, again, I cannot do 0.4 to the 1/12 on the top of my head. So let me do that really quick. So what I got here is rounded. It is 0.93. So I'm going to say, well, that's just equal to a to the 0.93, not to the, with the 0.93 base to the t. And now I've got to make this look like 1 minus r. So 0.93 is just equal to, and I'm going to write this in black. So my answer here is going to be y equals, that a stays the same. 0.93 is just 1 minus 0.07. to the t. So it's a lot of expansion, right? We're used to doing things the opposite way. We're used to sitting here and going, well, we want to make this as simple as possible, and then we do that and make it into this. But we're kind of going opposite in this case. We want to expand things. This is about as simple as it gets, but I don't want it to be simple. I want it to match whatever my equation is. So I've got to expand this t over 12 to be 1 over 12 times t, and then separate it. And then I've got to evaluate this, and then instead of writing it like this in its simplest version, 0.93, I want to expand it into being 1 minus 0.07. So it's a lot of expansion. It's a different way of thinking, but hopefully that makes sense to you guys. Okay. Then finally, coming down here to number 6, given the formula, y equals a times 1 plus r to the t, what would your bank account be equal to, I should say, what would your bank account have if you have a principal amount of $2,000 with an interest rate of 4.2% compounded weekly for 3 years. Okay, so this is kind of where things get a little tricky. Yes, you're just plugging in a lot of times, but this compounded weekly is going to be a big thing, okay? And actually what we're going to do here is rewrite this formula here, this guy right here, we're going to rewrite that right now. So I still have y equals, right? That's not going to change anything, but everything else I'm going to color code and label. So that a, you're going to see that a lot as p. That's your principal amount. So a is your principal. So that's your principal amount, your starting amount, your initial amount is that principal, right? Then we've got this 1 plus, right? That doesn't really affect anything, but we do have this r, and we're going to rewrite this so that it's r over n. That r is your interest rate, which is really simple, right? It tells us right there. That's not how you... Okay, so it tells us right there what your interest rate is. Your interest rate is 4.2. But the compounded weekly part is where that n comes in. So the n is going to be the increment of time. Let's see how do I word this. The amount of payments per year, right? So let's just say payments per year. That's a good way of putting it. Payments per year. And then finally that last thing up here is going to be the t. But the n is going to creep up here as well. So it's going to be n times the t, and that t is time in years. So we've really just got to sit here and plug everything in. And this is where, like I said, guys, this is going to be really weird to think about, but, you know, please ask us questions as we go. So the principal amount, we're just going to plug and chug. We're going to plug everything in and do this. So the principal amount is $2,000. So that's that A, that red A. So 2,000. And then I've got the 1 plus the R, my interest rate, is 4.2. But you do not put it as 4.2. You put it as 0.042 because that's the percentage in, you know, real decimals in real numbers. And then you're going to put that over in the amount of payments per year. Now that's where this compounded weekly thing comes in. How many weeks are in a year? If it's compounded weekly, then per year it's going to compound 52 times. That's how many weeks are in a year. And then you close those parentheses, and then you bring that 52 again up here. 52 times the time, which the time in years is 3 years. Remember, we got all those numbers from that little word problem up there. Okay, and then once you have that, guys, it's as simple as plugging it into your calculator, and there's no shame in doing that, right? So when you do get that answer, your answer is going to be, let's get the black one for this, so equals 2,268.45. So the amount of money you'll have in your bank account after 3 years is $2,268.45. So really, you've increased your value, you've increased your principal by a number of $268.45 over 3 years, right? So again, this is stuff that really just comes with practice. You should practice some regular, simple exponential growth problems. Then you should practice some of these that, You change the payments per year, whether it's weekly, monthly, biannually, which would mean 2 times, all that kind of stuff, quarterly. They all change it just a little bit. But remember, guys, if you have any questions, feel free to contact us. I hope you guys' week is going really well, and have a good one.